We've learned that homogeneous catalysis is when the catalyst and reactants exist in the same phase. But there is also heterogeneous catalysis, which is when the catalyst exists in a different phase than that of the reactants. Most often, the catalyst will be in the solid phase and is placed in solutions of liquids or gases, so that reactant molecules can approach the surface of the catalyst where the chemistry will occur. Heterogeneous catalysis will typically have 4 steps. First, the reactant molecules will be adsorbed onto the surface of the catalyst. Here it is a nickel surface, and we can see molecules of hydrogen being adsorbed onto the surface. Next, we can also see the substrate molecule of ethylene being lowered down onto the nickel, where it is adsorbed as well. In doing so, the carbon-carbon pi bond is broken, and carbon-nickel bonds are formed. Next, once the adsorbed reactant is activated, the reaction will take place. This is the part where the hydrogen atoms diffuse around the nickel until they find a substrate, at which point they will form new bonds to the carbon atoms. Lastly, diffusion of the product will take place, where it will detach from the nickel surface and return to solution. So the nickel surface was not used up in the reaction. It remains intact to facilitate another reaction, and it has lowered the activation energy of the reaction by giving the molecules something to interact with during bond cleavage, which stabilizes the intermediates of the reaction. This is why the activation energy is substantially lower than if the nickel catalyst were not involved. There are many industrial processes that utilize heterogeneous catalysis because of its convenience. The catalyst is in a different phase than the solution, so it doesn't need to be recovered after being used. It can simply be used as is again and again. We use this kind of method in catalytic converters in automobiles, as well as a method for generating sulfuric acid, ammonia, and methanol.